Okay, let's get restarted here and talk about the dehydration of alcohols. And dehydration is exactly what you would think it is, which is it is removing water from an alcohol. And what happens when you remove water from an alcohol, you end up producing a functional group that you're familiar with, which is an alkene. So if you think about it, hydration of an alkene produces an alcohol, and the dehydration of an alcohol produces an alkene. So they're kind of the reverse of each other. And it says here that dehydration is considered what's called an elimination reaction. Why? Because you're eliminating a small molecule called water. Yeah. A molecule loses atoms or ions from its structure in an elimination reaction. Here, you remove a hydroxyl and a hydrogen. When you combine a hydroxyl and a hydrogen, what do you get? You get H2O, right? Okay. And they eliminate from adjacent carbons. What does adjacent carbons mean? It means you eliminate the hydrogen and the hydroxyl from carbons that are next to each other. Okay, so you can't just pick them from random carbons in the molecule. They've got to be carbons that are adjacent to each other. And you end up producing an alcohol in water. Again, it's the reversal of the hydration reaction that forms alcohols. Now, if you're wondering, well, how do I know, when what's the difference? What's the difference? Well, let's look. If I go all the way back here to this addition reaction, okay, adding water to an alkene, look very carefully. Okay, you got to have a sharp eye here. But all you add was acid, okay, and you end up making an alcohol. Okay, sounds good. Let's go back here to the dehydration reaction. What did you add besides acid? It wasn't just acid. It's acid and what? Heat. Okay? And what does heat cause? Heat causes water, causes H2O to evaporate and leave the molecule. Okay? So that's the key difference, is that you're adding heat. All right, now let's look at how we figured out how to draw the alkene. I need you to pay very close attention to me here. Okay, you look at the carbonyl carbon. Okay, that's the one that I have in the blue box here. That's the one that's got the hydroxyl, okay? So we're trying to find the atoms to make H2O, okay? H2O, so we need two hydrogens and an oxygen. So far, in my blue box, I've got a hydrogen and an oxygen. I need to get another hydrogen. Where can I go to get that hydrogen? Can I go over here? No, I have to go in the molecule, and I have to go to an adjacent carbon. There is only one adjacent carbon in this molecule, and it's this carbon right here. It's next door neighbor. There isn't one here, there isn't one here, and there certainly isn't one here. There's only that carbon that I have highlighted in yellow. So that means I can take the hydrogen from here. Now, if you put the box around, if you put it around this one here, it doesn't matter. You're going to get the same answer. But I need a hydrogen, so I'm going to pull it from here. So now I have all the atoms that I need for my H2O. So when I draw my alkene, I'm going to draw what's left over, and I'll kind of go through it here quickly. You would have the R group, the carbon that I had highlighted in yellow, the other carbon on the end. You have this hydrogen, and this hydrogen, and you've lost this hydrogen and the hydroxyl. What are you going to replace them with? You're going to replace them with the double bond. So what I've drawn, this alkene that I've just drawn right here, is the exact same as that alkene right there. Give me a thumbs up if you follow me on that. Adjacent carbon, removal of hydrogen. All right, good, great, as they say in Scottish, perfect. Well, what happens when it gets more interesting? When you have more than one adjacent carbon? Ooh, it gets a little trickier then. So it says here that some alcohol dehydration reactions produce a mixture of products. And in that case, we don't use Markovnikov's rule. We use a rule developed by another Russian, and his name is Zaitsev. Okay, so everybody's got to know Zaitsev's rule. And Zaitsev's rule is this. It states that in an elimination reaction, what's the elimination, right? Losing H2O to form an alkene. In that elimination, the alkene with the greatest number of alkyl groups on the double bonded carbon, I should say double bonded carbons, anyhow, is the major product of the reaction. Let's watch, okay? I need you to pay very close attention here, okay? If we look at 2-butanol, okay, we're starting with 2-butanol here and here. Now, they've highlighted, they actually drew it the same way both times, but anyhow, let's go through it quickly here. If we look at the 2-butanol that I have highlighted, okay, that I have the name highlighted, here is the carbonyl carbon. It has OH attached. I need to get a hydrogen. Where can I get it? I'm going to go to the next door. There are actually two next door or adjacent carbons. There's this one here, and there's this one here. Now, in the first example, the one we're doing here, they took the hydrogen from this carbon that I have highlighted in yellow. So now you have your H2O. Okay, I'll box it in red so you know where they're coming from. So that means when you draw the product, the double bond is going to be between these two carbons. Right? Notice it's right in the middle. So you end up with this molecule, 2-butene, plus you get water. Okay? So that's the first product. All right. The next reaction, same molecule, 2-butanol, but now we look at the carbonyl carbon. We're going to ignore that carbon. Okay, we're going to look at all the possibilities. And there's another next door neighbor right here. It's got 3 hydrogens attached. Now it's drawn condensed. There's 1, 2, 3, right? They just drew it as CH3. But if we remove one of those, we end up with a CH2. So if we took one of the hydrogens from here and this hydroxyl, we would draw the double bond between these two carbons to make this double bond. And we would have what's called 1-butene. And you're eliminating water in both cases. So in both reactions, you end up with the alkene and water. Give me a thumbs up if you follow me with that, okay? Because we still haven't discussed Zaitsev's rule. But just finding the products. Do you think you could find the products? Draw them out. All right. Thanks, Madison. All right, good. Okay, we're that far. Now I need you to understand what is the Zaitsev product and what is, the other product, okay? So the major product in this case is called the Zaitsev product, okay? The other product, I don't think the name is in our textbook, but if you're one of those people that has an inquiring mind and you need to know, it's called the Hoffman product. Okay, it's named after somebody named Hoffman. Let's examine 2-butene and 1-butene and determine why 2-butene is the major product. I'm going to draw an expanded structure of 2-butene, okay? So it's a carbon with a hydrogen, methyl group, double bond, another hydrogen. Okay, so there's 2-butene. Okay, now I'm going to draw 1-butene. So I have carbon, hydrogen. Oops, I wanted to draw the whole bloody thing out for you. Pardon my language. Like this. CH3, CH2. Okay, let's examine these two alkenes that I just took so much time to draw. Which one of these carbon-carbon double bonds has the most alkyl groups on it? 2-butene or 1-butene? Which one has the most alkyl groups? Okay, so people are saying 2-butene. You're right. Let's examine it very carefully. Look, here's the carbon-carbon double bond. Here's the carbon-carbon double bond. 2-butene has one methyl group and another methyl group. That's 2 alkyl groups attached totally. 1-butene has one ethyl group and that's it. Okay, so 2-butene is the major product because it has two substituents. 1-butene only has one substituent. And so The one that has the greatest number of alkyl groups is called the Zaitsev product. That's Zaitsev's rule. Okay, so this is the Zaitsev product. Does that clear it up for the people who are confused? Give me a thumbs up if it clears it up a little bit. Bum, 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 bum. Okay, somebody said okay. All right. All right, good enough. Okay, so that's Zaitsev's rule. All right, Zaitsev's rule. Great rule. Okay, here's another example. It says here, what are the major and minor products when 3-methyl-2-butanol is dehydrated? Zaitsev's rule, this is just repeating Zaitsev's rule, is nothing more than that, states that in an elimination reaction, the alkene with the greatest number of alkyl groups on the double bonded carbon is the major product of the reaction. Okay, I'm going to go over this one again very carefully with you. Let's analyze very carefully. So we have the carbonyl-carbon. We have a hydroxyl. We've got how many carbons that are adjacent? 1, 2. We're going to start with the one on the left. So that means that we would take our OH from here, and we would take our hydrogen from here. So that means that in the product, we're going to draw the double bond between these two carbons right there. And so that would give us this molecule, which is 3-methyl-2-butene. Okay? We do the exact same exercise all over again. Now we look at the other next door neighbor. So we would pull our OH from here, and we'd pull a hydrogen from here. Then we'd have to draw the double bond between these two carbons. Okay, so now that we've drawn the two products, which one of them is the Zaitsev product? Now it already tells us on here. But look, if I look at this carbon-carbon double bond and this carbon-carbon double bond, I'm going to circle this molecule in green. And I want you to tell me, how many alkyl groups are attached to that carbon-carbon double bond? How many total alkyl groups are on that carbon-carbon double bond? I see 3, 3, 3. The threes have it, right? There are 3 alkyl groups. 1-methyl, 2-methyl, and a 3rd methyl. There are 3 alkyl groups attached. Okay, now let's back up. We'll delete that, and let's examine the other product. I'll circle it in yellow. How many alkyl groups are attached to the carbon-carbon double bond in this molecule? You're right, it's only 1, okay? It's 1. Don't fall into the trap of, oh, it's 3 carbons, it's 3 groups. No, it's 1 group. It's just an isopropyl group. So it's got 1 carbon directly attached to it. It's got this one whole substituent. That's it. It's got, look, and if you're unsure of yourself, double check. You've got 1, 2, 3 hydrogens. So it must be just 1 group. All right. Give me a thumbs up if that, clears things up. Zaitsev's rule. You're ready to go. Hand me the second exam. Let me knock this thing out of the park. I'll be ready by 8 p.m. tonight. Okay. All right. So Zaitsev's rule. There we go. So let's recap, some of these reactions. We've talked about hydration. So I'm not annoyed. What are you talking about? Anyhow, no, I'm not annoyed. I'm just trying to explain it. Anyhow, why would I be annoyed? It's not my grade. Anyhow, so let's cover the reactions that we've looked at this evening. We've looked at preparation of alcohols with a hydration reaction. That's something that we already covered in the alkenes chapter. We already studied Markovnikov's rule. We look at hydrogenation, okay? Hydrogenation is a reduction reaction because you're adding hydrogen across an aldehyde or a ketone. We looked at a dehydration reaction, and I explained to you what dehydration was and how you need heat to do that. And I explained to you what Zaitsev's rule is. And we looked at Zaitsev's product. Okay, so you should be able to identify the major and minor products when you do an elimination reaction, okay, a dehydration reaction. All right, well, let's switch gears entirely and talk about an oxidation reaction, or the oxidation of primary alcohols. Remember, I told you earlier on this evening that oxidation is gaining oxygen or losing hydrogen. Right? Remember reduction? Reduction was gaining hydrogen or losing oxygen. All right. All right. So it says here that primary alcohols usually oxidize to carboxylic acids. Here's a primary alcohol. We already discussed why this is primary, and it is because the carbonyl carbon only has one carbon attached to it. When you take a primary alcohol and oxidize it, we use the symbol O in square brackets to represent an oxidizing agent. Common oxidizing agents that are used in organic chemistry are KMNO4 and hydroxide. So KMNO4, that's potassium permanganate. So potassium permanganate in base or hydroxide. And then also this one here. This is called chromic acid. But again, instead of writing all those out, a lot of the time we just use O like that. Now, if you're wondering, like, why do you have two different ones highlighted? Why do you have potassium permanganate and hydroxide and chromic acid? The reason why is because hydroxide is a base and chromic acid is obviously an acid. And so sometimes in organic chemistry, you might have to do the reaction such that you need to do the reaction in acid, and other times you might need to do a reaction in base. And so it's good to have both of those under your hat. In fact, a good organic chemist, he or he will always have many ways of doing the same reaction. All right, so if we take a primary alcohol, if we oxidize it, what happens in oxidation? We lose hydrogens and we gain oxygens. Well, you can see that we didn't gain any oxygens here because we started with one oxygen and we end up with one oxygen. But did we lose hydrogens? Oh, you bet your bobby socks we did. We lost both of these hydrogens are gone, okay, from the molecule. So you lose these two hydrogens, you combine it with an oxygen from the oxidizing agent, and what does that give you? It gives you H2O. So you're going to form water. What else? Well, now what you've got left over is you have your R group, your carbon, a hydrogen, and one oxygen. Carbon always has 4 bonds, and so you have to make a double bond between the carbon and the oxygen like that, which would produce an aldehyde. All right, so that's the oxidation of an alcohol. Now, something that it says here at the top, it says that primary alcohols usually oxidize to give you a carboxylic acid. An aldehyde isn't a carboxylic acid, so let's talk about that more. Okay, it says here, write an equation showing the oxidation of 2,2-dimethylpropanol to produce 2,2-dimethylpropanol. Again, same exercise that we just looked at. Here's your carbonyl carbon. Remember, you're going to combine 2 of the hydrogens and oxygen from the oxidizing agent to make H2O. And then you're going to form a double bond between the carbon and the oxygen. That's this double bond right here. Okay? The thing about this reaction is that usually an aldehyde will keep reacting. It's kind of like a runaway train, and it will keep reacting, and it will form a carboxylic acid. So let me show you what the carboxylic acid formed would be. You would have this, and then you'd have your carbonyl, and then you would gain an oxygen like this. So you'd end up with an oxygen in here to form a carboxylic acid like that. But there are reagents you can use to just get the reaction to stop like this, to stop at the aldehyde. Okay, reactions of secondary alcohols. This is a little bit simpler. It says there the secondary alcohols, and you should know what a secondary alcohol is. The carbonyl carbon is attached to 2 R groups. A secondary alcohol always oxidizes to give you a ketone. Why? Because you lose 2 hydrogens. It says this reaction is also an elimination of 2 hydrogens. Remember what I told you earlier. Losing hydrogen is reduction. No, I didn't say that. Losing hydrogen is oxidation. I'm getting tired. Anyhow, losing hydrogen is oxidation like that. So we're going to lose 1, 2 hydrogens. Those are going to combine with the oxygen from the oxidizing agent to make water. And then you're going to make a double bond between the carbon and the oxygen to make a ketone, just like that. Okay, so you got to be able to know that, again, a primary alcohol gives you an aldehyde, and an aldehyde can be further oxidized to give you a carboxylic acid, and a secondary alcohol will oxidize always to give you a ketone. Now it says here, tertiary alcohols do not oxidize, and there is no exception to this. Tertiary alcohols don't oxidize at all. So we could summarize right here. A primary alcohol gives you an aldehyde, then a carboxylic acid. Secondary gives you a ketone. A tertiary alcohol, no reaction. It will never oxidize. And the reason why is because in order for oxidation to occur in any molecule, the carbonyl carbon has to have at least 1 hydrogen in order to oxidize. And you can see there's no hydrogen here, none here, and none here. So nothing happens. And I can tell you that, you know, there's a lot of things in chemistry that have exceptions, a lot of rules with exceptions, but this is one rule for which there are 0 exceptions. So you don't have to worry about exceptions at all in this, at all. Every time you see a tertiary alcohol and somebody writes oxidation, you write no reaction and you'll get full points. Okay, oxidation and reduction in living systems. I'm not going to really ask you a whole lot about this, but I just want you to know a couple of things that you should have learned in general chemistry. You might have learned this expression here, oil rig, and that deals with electrons, okay? It deals with electrons, and it is oxidation is losing electrons, and reduction is gaining electrons. Another version of it is, the Canadian version is Leo, the lion says Gur, which is lose electrons oxidized, gains electrons reduced. Anyhow, these kinds of changes though, where we start counting electrons, and you probably did that in Chemistry 101 if you took it at PPCC, these are usually done in inorganic chemistry, okay? When you have ions, right? If you think about, you know, taking a sodium, right? If you have solid sodium and you get a sodium cation, okay, plus an electron, well, we call that oxidation, right? Because the sodium loses an electron. And then if you have chlorine, right, it can gain electrons to produce 2-chloride, right? These are things that you've probably done, and that's reduction. So we could even highlight that. This is reduction. This is oxidation. And then you learned how to label oxidizing agents, reducing agents, right? Those are things that you did in Chemistry 101. Now, in organic chemistry, in organic systems, it's actually a little bit more difficult to determine whether oxidation or reduction has taken place, as there might be no change in charge. Think about it. Tonight, we haven't looked at any charges in any molecules, right? We didn't see any cations, any anions until I just drew these two just now. And so that's why I taught you the whole gaining hydrogen, losing oxygen is reduction, and losing hydrogen and gaining oxygen is oxidation, because it's a very quick method to determine whether you've got oxidation or reduction. So in organic systems, we track it like this. And again, I've gone over this with you already a few times tonight, what oxidation and reduction are. So if we look at the alcohol, if we go from an alcohol to an aldehyde to a carboxylic acid, why is this oxidation going in this direction, right? Because if we go from an alcohol to an aldehyde, we end up, right, we lose these 2 hydrogens. As we go from the aldehyde to the carboxylic acid, we didn't lose any hydrogens, right? We still have 1 hydrogen, but what did we do? We gained an oxygen, right? We gained this oxygen right here, okay? And so that's the kind of mindset you want to have in this class when we're talking about oxidation and reduction. Anyhow, later on, we're going to look at biochemistry in probably the last 1/3 of the course. And you might have heard of nicotinamide adenine dinucleotide, or NAD+, which is a coenzyme that's commonly involved in redox or oxidation reduction, what we call redox reactions in biochemistry. So here we have a molecule called malate. You don't have to worry about malate right now, but the idea is that NAD plus is getting reduced here. And how do I know? Oops, I didn't mean to do that. How do I know that NAD plus is being reduced? Because the NAD plus is being converted into NADH. And what did I tell you? That H stands for hydrogen. So this is being reduced, right? So this is reduction, okay? And you can't have oxidation or reduction without the other, okay? So cannot have reduction without oxidation and vice versa. You can't have oxidation without reduction, okay? So if NAD plus is being reduced, that tells you that malate must be being oxidized. Let's double check. Well, you can see that not only did the malate lose 2 hydrogens, but it also gained a bond to an oxygen like that. So this is being oxidized, okay? So we'll always have to keep in mind oxidation and reduction a little bit in this class, even when we get into biochemistry later on. All right, let's switch gears and talk about this molecule called phenol. I asked you to learn the name of this compound earlier on in the class. I said you need to know the names of a few common aromatic compounds. I said you need to know the name of the 6-membered ring with alternating double bonds. This is called benzene. And I told you that when you have an alcohol or a hydroxyl on your benzene like this, it's called phenol. Okay, phenol actually has an old-fashioned name, which is carbolic acid. Anyhow, it says here that phenols are compounds in which the hydroxyl group is attached to a benzene ring. They're polar compounds. Why? Because they have a hydroxyl group, right? I told you earlier on this evening when we talked about electronegativity, right, that oxygen is more electronegative than carbon, and so we have a dipole going this way and we have a dipole going that way. You could also, say, well, the oxygen has a delta minus, the hydrogen has a delta plus, like that if you want. Simpler phenols are somewhat water soluble. Remember, I told you the cutoff was 4 carbons. Now that's not some kind of hard and fast rule that Moses came down from the mountaintops with. Okay, that's just sort of a rule of thumb. So if you have a phenol, generally speaking, they're somewhat water soluble. They're found in all kinds of places in everyday life, like flavorings and perfumes. And they have the formula aromatic. So the AR does not stand for argon. This AR stands for aromatic. Okay. And then a hydroxyl. So it says here the AR must be an aromatic ring like benzene. Okay, so that's a little bit about the structure of phenol. There's all kinds of phenol derivatives. I'm not really going to quiz you on, the memorizing the names of any of these. I've never done it before, so I'm not going to start now. You see that here we have a phenol here, and this molecule, hexachlorophene. This is called hexylresorcinol here. It's an antiseptic. Orthophenol here. Anyhow, these are, again, widely used as disinfectants and antiseptics, germicides. So basically, things that are used widely in healthcare to keep, buildings and patients and equipment and clothing and, surgical tools to keep everything sterilized. So that's what phenol derivatives are used for. And as I told you, phenol has the old name carbolic acid. So when you have a solution of phenol in water, it's called carbolic acid. What else? Let's move on and talk about ethers. Ethers have this general formula where you have an oxygen sandwiched in between 2 R groups, and the R groups could be aliphatic, they could be aromatic. One of the most common ethers that's used in organic chemistry is this one here. If you have an ethyl group and then an oxygen and then another ethyl group here, this is diethyl ether, a very commonly used ether in organic chemistry. It says here the ethers are slightly polar due to the polar carbon-oxygen bond, right? I told you that oxygen has an electronegativity of 3.5 and carbon has an electronegativity of 2.5. So the difference in electronegativity between the two is 1.0. So we have a dipole, and we could draw the dipole like this. Okay, we could draw the dipole over here like this. So something else that I haven't addressed tonight is that you should know this from organic or general chemistry 1, that when you draw the dipole like this, you take these vectors and you add them together, okay? And so the net resultant vector would be something going straight up like this. And this shows you the direction of the dipole. All right, this molecule that's shown here, this is dimethyl ether, which is CH3OCH3. I told you earlier on in the class, I used this as an example when I was talking about constitutional isomers. Dimethyl ether is used as a propellant in spray paint. All right, let's talk about the physical properties of ethers. Earlier on this evening, we took some time to take a look at these two compounds. We looked at butane and we looked at 1-propanol, and we compared them. We said they have similar molar masses. And then we looked at the differences between their boiling points. And we said, well, butane only has London forces. And then we said, well, the propanol definitely has London forces because all molecules have London forces. And then we said 1-propanol also has dipole forces because there's a dipole between the carbon and the oxygen and the hydrogen and the oxygen. So we said it's also got dipole forces. But we said what makes 1-propanol have this really high boiling point is that it has the capability to do hydrogen bonding. Okay, and so it has this really high boiling point. Well, if you look at ethyl methyl ether, which has a molar mass very similar to the other two, you see that its boiling point is somewhere in between, right? It's higher than that of the alkane, but it's lower than that of the alcohol. And the reason why is because the ether, of course, experiences London forces, but it also has dipole forces. It does not have hydrogen bonding by itself, right? Because again, in order for hydrogen bonding to occur, a molecule has to have a bond between hydrogen and oxygen, a bond between hydrogen and nitrogen, or a bond between hydrogen and fluorine. And I don't see any bonds between this oxygen and a hydrogen, a nitrogen, or a fluorine. Okay, and so that is why it's in between. Now, something that you will be asked to do probably on the next exam is to rank compounds in order of boiling point. And so you have to be fully aware that an ether will boil, if you compare an alkane, an ether, and an alcohol of similar molar masses, that the ether will boil somewhere in between the alkane and the alcohol. Common names of ethers. Again, common names are very commonly used. The good news is that common names of ethers, I don't like to use the word simple and organic chemistry together, but I would say that this is one of the easier things that we learn in nomenclature. It says here the common names for ethers consist of the names of the two groups attached to the oxygen, put them in alphabetical order, throw the word ether on the end. Done. Okay. So you can see that I have two methyl groups in this first compound. So I would call this dimethyl ether. Something that's not mentioned here in the rules is that sometimes scientists will shorten it even more. They'll just call it methyl ether. They're implying that both groups are a methyl. Here you have a methyl and an ethyl. Well, you alphabetize, E comes before M, so it's ethyl methyl ether. Now they say here that it's alphabetical order or by size. This whole going by size thing, I've never seen it anywhere except for in this book. Okay, so I don't know if you peruse around the internet how common that is. So it goes from small to large. So if you look at the two groups, methyl is smaller than ethyl. So they're saying that based on this rule, you could call it methyl ethyl ether too. Anywho, what else? We have the next one, which is we have an ethyl group. We have an ethyl group over here, and we have an isopropyl group here. Well, whether you do it according to alphabetical order or by size, either way, you end up with the same name. Okay, so there we go. Iso doesn't take priority. No, because we ignore all prefixes except iso, cyclo, and neo, right? E comes before I. Whoever said E comes before I in the alphabet, right? Anyhow, there we go. Let's just delete this. There we go. All right, but when it comes to larger ethers, more complex ethers, you're going to have to use IUPAC nomenclature. And the good news is that you can borrow some of the rules that you learned in alkane, alkene, and alcohol nomenclature. So here it is. It says the IUPAC names, or the International Union of Pure and Applied Chemistry names for ethers, are based on the alkane name of the longest chain attached to the oxygen. And then the shorter chain is called an alkoxy. You're like, what do you mean by an alkoxy? Well, if you have ethane and you put an oxygen on the end, you get an ethoxy. If you have a methyl group, for example, right? If you have a methyl and you put an oxygen on the end, you have a methoxy. Okay, if you had an isopropyl group like this and you put an oxygen on it like this is actually called an isopropoxy. If you had a butyl group, 1, 2, 3, 4, and then an oxygen like this, you'd call that a butoxy. I don't know what butoxyl is. Butoxy. If you have a tert butyl in an oxygen like this, that's pretty common. You call this a tert butoxy, like that. Okay, so on and so forth. So if we look at the example that's shown down here at the bottom of the slide, the longest carbon chain is shown right here. Okay, and then what do we have on it right here? We have a methoxy group. Methoxy. Okay, and it's on the first carbon. So this must be 1-methoxy pentane. Okay, we got 9 minutes left. Let's see here. I just want to see where we are. Yeah, we're almost done ethers. Let's just look at a few more slides and then maybe we'll call it a day. It says here the reactivity of ethers. It says chemically, ethers are moderately inert. Okay, and you might be thinking, well, that's kind of boring if you can't do much with an ether. Well, what I'll tell you is that the fact that they're chemically inert or moderately inert, okay, means that they make good solvents. So ethers are very commonly used as solvents in organic chemistry because they don't react, generally speaking. It says they don't normally react with reducing agents or bases. They're extremely volatile. Does anybody know what volatile means in chemistry terms, or have an idea what it means? What volatile might mean? No? Volatile means it has a very low boiling point. Okay? Another way to phrase this would be a high vapor pressure. Okay? High flammability, so they catch on fire very easily. Anyhow, how might you go about making an ether? Well, there's a really easy way to make an ether. In fact, I told you earlier on that diethyl ether is a very commonly used ether in organic chemistry. You can make a symmetrical ether, and it's symmetrical because it's the same on both sides of the oxygen, by taking 2 molecules of an alcohol and treating them with an acid catalyst and with heat. What does heat do, right? It removes water, okay? So that's why you end up with water as a product. So it's, in essence, a dehydration reaction, right? What are you removing from the 2 ethers? You're removing H2O. So then what's left over is you're going to be left with R and RO, right? Right there, okay? And you're left over with H2O. So diethyl ether is actually produced on like the ton scale in America every year, and I think that's how they do it. They take ethanol and just treat it with an acid catalyst and heat it up. Medical uses of ethers. If you've ever been to the doctor and been put under anesthetic before, you've probably heard, or maybe you've heard of ether being used as an anesthetic. Well, it's a really old anesthetic, diethyl ether, because I know it works as an anesthetic, but I think it made people very sick, caused a lot of nausea. And so another problem is that it was highly flammable, so that's also not good. It says here that ethers are often used as anesthetics They accumulate in the lipid material of nerve cells and interfere with nerve impulse transmission, which allows you to not feel anything when you're put under anesthetic. Anyhow, it says here that halogenated ethers are used routinely as general anesthetics. Why have all these different ethers been developed? Well, it's because they're less flammable and they're much safer to work with. So we have enflurane, isoflurane, sevoflurane, desflurane. These are commonly used ethers that are used, again, as anesthetics nowadays. All right,